All right, force assessment quiz. So this is a video just outlining the solutions to the quiz that you would have practiced. And again, I got to emphasize that you need to go through the quiz first, try as best you can, and then go through the solutions afterwards. To visit the solutions now and then go back to the quiz is not going to be really a good learning experience. So you need to be able to take the quiz, take your solutions, compare them to this video, and then just assess where you're having difficulties, and then seek extra help if you're still having questions. So for the first question, we're looking at that free body diagram, and in this free body diagram, it's asking you to look for or calculate Fnet, normal force, acceleration, and frictional force. The data that's provided for you is it gives you the mass of 1,500 grams. Now that needs to be changed to kilograms. That would be one area where sometimes there's a misconception. So anytime you're using F equals ma, mass must be in kilograms, so it really should be 1.5 kilograms. Gives you a frictional coefficient, a kinetic frictional coefficient of 0.13, and then it gives you an overall applied force of 3.6 newtons. So again, your normal force is equal to your gravitational force, and that'll always be the case on a horizontal surface. So then we've gone through that calculation. Again, we've used our 1.5 kilograms, multiplied it by our acceleration to gravity. So rounded, we have a normal force of 15 newtons. Using that normal force now, we can now calculate our frictional coefficient, and so that's where we're getting our 1.9 newtons. So we're going to be using this 15 newtons down here, so that's just the unrounded number, that 14.7, and so we're rearranging our frictional coefficient equation to figure out our kinetic friction. So remember that frictional force and kinetic friction are the same number, so that's where we're getting our 1.9. Once we have our 1.9, we can then use our relationship, our Fnet equals Fa minus Ff. This was given to us in the question, 3.6, and then we just calculated our 1.9 for our frictional force. The difference between those two numbers is our Fnet. Now remember, our Fnet is to do solely with acceleration. And so now we can use that number into our Fnet equation. And again, we have our mass of 1.5, and that allows us to calculate our 1.1 meter per second squared. So that would be your typical free body diagram. And again, that would be something that would be possibly on a test or an exam. Now, for the second question, we are dealing with explaining what the outcome between two objects is using the third and the second law. And in this particular case, it's asking you, who will travel further. So you're really just justifying that. You don't need to come up with any specific numbers. You just need to explain, in terms of some of the kinematics that would happen due to the force interactions, which one would end up going further. So you want to start off with the third law, because the third law dictates where the forces are coming from, and most importantly, it tells you that the forces are equal. They're also opposite. Now, in this particular question, we're not really dealing with the direction, so that part of it doesn't really have to be there, but this part here is key. So you definitely want to talk about how Mike is an action force, so the AF is the action force on Frank, so that's the initial force. The response to that force is the reaction force, so that's Frank on Mike. Now, the third law again establishes that it is equal, which then allows us to talk about the second law. And so you want to use what you've established in your third law to help explain the relationship that's established in the second law. So we want to almost restate that, yeah, since the forces are equal, and I've just put in brackets here that, this is due to the third law, and I would suggest that you do that in your test or your quiz or any kind of solution that you do with these types of questions, just to show that you see where that link is, and that is then equal. And because we have established that, and again, this is what we established in the lab, right? We had those two parts in the lab. When forces are equal, then there is an inverse relationship between mass and acceleration, right? So then we can go on and we can state, yeah, because there is a mass difference between Mike and Frank, and the second law states that if the force remains the same, and that's key, when you're talking about a relationship, you have to state what stays the same. We can state that that stays the same because of the third law, then there is an inverse relationship between acceleration and mass. That allows us then to, state what that outcome is going to be. This means that Mike will accelerate less than Frank, given that they're on the same surface, because of that mass difference. And because they are accelerating less, then there is less distance covered between the two. Now, you don't have to go through and explain that with numbers and so on. It's just assumed that because you accelerate less, you're really going to reach a lower maximum velocity or speed. And because it's on the same surface, that means that you are just not going to travel as far. And so when you glide to a stop, your max speed is going to be less between Frank and Mike, and that's what's going to cause them not to travel as far, or might not travel as far. So if I go back to this question, where you get your marks from, absolutely you need to establish, it's a question out of 5, so you have to establish the action-reaction force. Like, where are these forces coming from? Which one's action? Which one's reaction? The second mark is definitely coming from the idea of forces are equal. And whether you state that up in that third law or whether you establish that down in the second law, you need to emphasize and clearly state that these forces are equal because of the third law. So that's essential to state. You want to bring out the explanation that, yeah, there's definitely a mass difference between the two objects, so between Mike and Frank. And then you want to state what that relationship is. It's an inverse relationship between mass and acceleration. And again, the only reason you can say that is because you've stated that they are equal. And then the last mark is really just coming from, and I know I've written a lot here, but really just kind of summarizing less acceleration. Because Mike has less acceleration, he's just not going to travel as far as Frank because of that mass difference. Make sure that you answer the question. The question's talking about who will travel further. I'm not asking about what direction they're going to end up. So you don't need to talk about opposite forces in this case. Just focus on what the question is answering. And again, it's a justification question, so you want to write information that allows you to explain or justify or show me, because I'm the one that's marking it, that you understand how the third and the second law work together. For the next question, what is net force? Net force, and again, this is a 2-mark question. Net force is directly, and you got to explain that, directly, it's the force that's directly or solely causes acceleration, those 2 points there. So it is due to acceleration, but it's the force that there's no other components to it, right? It's whatever, if you had 200 newtons, that all of that 200 newtons goes right into acceleration. And that's a big difference between net force and that applied force. Question number 4, just a simple rearrangement of F net. Again, you just want to make sure that you're in meters per second squared. You want to make sure that you're in newtons, and then you're going to rearrange that, and that mass is going to be 25 kilograms. Difference between static and kinetic friction. So SF, not San Francisco, but static friction. Static friction is what prevents an object from moving. Right? It's not starting friction is the amount of force required, or the friction that's present just to get the object going. When we talk about static friction, we're just talking about what prevents an object from moving. Kinetic friction is the opposing force that is in the opposite direction of an object in motion. So whatever direction that object's moving, we always put that frictional force in the opposite direction. And those are two key components for that question. The next question is talking about, it's a calculation question, and you're going to be using kinetic coefficients, and it's kind of a break off from that skateboard question, and you will get a question like this on a test and an exam, where you're going to have to combine the idea of forces, F equals ma, coefficients of friction, and also some kinematics. So in this particular question, we have a box that is 4.5 kilograms. It's moving across a rough surface. So the key there, it's being pushed or moving across. So we're talking about kinetic friction. And so again, in there it says a constant force of 10 newtons. So again, we don't know, unless it otherwise specifies, that constant force is really your applied force. And again, that's a terminology item that you need to pay attention to when you read through these questions. So constant force, so that's really your applied force in this case. So given a kinetic friction, so the first part, again, you can start off in different areas, but the area that I'm going to start off with is figuring out my normal force. And again, normal force on a horizontal surface is equal to the gravitational force. And so now I've calculated that my gravitational force is 44.1. So really my normal force is 44.1 newtons. Again, that's not rounded. But now that I have my normal force, I can then use that into my kinetic coefficient equation. And again, just to emphasize, Fk is really equal to your frictional force. It's just another term, right? It's kinetic just means moving friction, and frictional force in this case is that moving object. So we can calculate how much frictional force is by using our kinetic coefficient equation. And so we can plug all that information in. I'm not going to go through all that, but we're going to end up with an Fk, which is really your frictional force. So frictional force is 7.94 newtons. Now, I can use that information to now figure out my F net, because in the question it states that we are at 10 newtons, right? That's that constant force, or that constant applied force. We just calculated our frictional force from using our frictional coefficient, and so the difference between those two is our F net, and this is all to do with acceleration. Because that is solely to do with acceleration, then we can plug that information into our second law. This is really the second law, and we're focusing just on F net. Now remember, our second law can calculate frictional force, it can calculate our gravitational force, it can also calculate our F net. So the force that we are dealing with in this case is to do with acceleration, so that's why we define this as our F net. It's a positive acceleration. So in this case, we're going to plug in those numbers, right? So we got our F net, that's what's coming from our previous calculation. That's 2.06, the difference between our applied force and our frictional force. And then we're going to divide that by our mass, which is our 4.5. And so this is our acceleration. So this is the acceleration that's occurring during that first phase. And so now we can use that acceleration a little bit later on. Alright, so our acceleration, again, what we calculated previously was our 0.458 meters per second squared. Now I'm just going to flip back to our last slide, and I think that should be over here. Right, so I just messed up that slide, so that should be 0.458 meters per second squared. So again, we're going to use that number in our kinematics equation now, and that's going to allow us to calculate what our initial velocity is. So we're going to use our F squared equals VI squared plus 2 times acceleration times displacement. We're going to rearrange that for VI. So this is coming over, and we're kind of switching spots there, so that's why we're getting a negative there, or subtraction. And so we are starting off with 2 meters per second. That's our final velocity, is 2 meters per second. And then we are going to then subtract that from our acceleration times our displacement. And so we're going to end up getting our initial velocity of 15 meters per second. Now, just to review that, again, this number is coming from the question, right? So we know that that's our final velocity because it states that the object reaches a speed of 2 meters per second. And again, the other 2 here is coming from the distance it actually travels. This is from our calculations, right? So we went through our F net, calculated our acceleration from that, and then that's where that information is coming from, that 0.458. And so then we're finding the difference between those 2 numbers, and that's where we're getting our 1.5 meters per second squared. Now, the last question is dealing with, again, something similar to the skateboard question, just some different variables thrown in here. So when we look at this object, we can break it down into section A and section B. In section A, we know it starts from rest, so we know it starts at 0 meters per second. We know it travels for 50 meters, and we know that it's F net, so a little bit different. This is giving us our F net, so again, that is all to do with acceleration. It's not a constant force. It's not an applied force. It's now stated that it's an F net, so we know that that 500 newtons is directly causing whatever acceleration rate that is in the question. We also can assume that because there's 2 sections to the question, so we have A and then B, that transition from A to B, we know that the final velocity of A is going to equal that initial velocity of B. For just section B, we know that the time that the box slows down for is 45 seconds, and then we know its final velocity is 0. Now, we can use that information to now calculate various components. So in the first part of the question, we know that our F net is given, right? So we know that it's 500 newtons. And so we're going to rearrange that, so we're going to bring mass over to the other side. And so we know now it's 500 divided by 100. So our acceleration rate for really section A is 5 meters per second squared. Now, As I stated earlier, we know that the initial and final velocities of section A and B, that number, is going to be the same. So if I just go back one here, so again, that's what I'm talking about here. So I know if I figure out the final velocity here, it's going to be my initial velocity for B. So I'm going to use that knowledge to help me solve another part of the question. So that's why, this is kind of stage one, step two, or stage two. We are now going to figure out our final velocity, and this is the final velocity of A. And again, that's going to equal our initial velocity of B. So this 22.36, which is unrounded, can then be used for our initial velocity for section B. So that really lets us go to stage three, or step three. We can now use an acceleration formula. So again, that 22.36, that is really now our initial velocity of section B. We know that it slows down over 45 seconds, so it's just giving us a time, not a distance. And so the acceleration rate is 0.497 meters per second squared. It's a negative because it's slowing down. Now again, it's negative, and so if I was going to calculate another kinematic portion of the question, I would use that negative in that calculation. However, I'm shifting over really to step four, or stage four, and we're now calculating frictional force. And again, forces, we're just going to keep positive. We know that this force is going backwards because it's a frictional force. It's opposing the motion of the object. So again, we're going to use that initial mass, which is 100 kilograms. We're going to multiply by the acceleration that we calculated in step three, and that allows us to calculate our frictional force. So that's frictional force that is for section B. So remember, anytime an object is sliding to a stop or coasting to a stop, there's no other force acting on it besides friction. And so the acceleration that is happening due to the sliding or coasting to a stop is solely due to frictional forces. And so then we can use the acceleration rate as it coasts to a stop, or as it slides to a stop, in our calculation of our frictional force. And that's why we can use this number here to calculate our overall frictional force. Then we're going back to our overall interaction between F net, frictional force, and applied force. So remember that this comes really from F net equals Fa minus Ff. I've just dropped the absolute value bars, and then we're just rearranging that for Fa. And Fa is always the sum of our F net, which is the force required for acceleration, and our frictional force. We know the frictional force that's present in the question is 49.7, and then so we know our overall applied force is 550 newtons. So these last two questions, questions 6 and 7, are definitely two different ways of calculating frictional force. Question 6 is calculating frictional force because, or through the method of frictional coefficients. Question 7 is calculating frictional force through the knowledge of knowing when an object's sliding or coasting to a stop, that acceleration rate is due only to frictional force. So if I use my Newton's second law, and I can calculate the acceleration of that phase, and then multiply it by that mass, I can calculate the frictional force that way. So you want to pay attention when you're going through these questions. How do I calculate frictional force? How do I get that acceleration rate of that frictional force? Sometimes it's through frictional coefficients. Sometimes it's through just understanding how the problem's laid out, and figuring out what that coasting or sliding section is.